starting week 3 already of the semester, right? Isn't that what it is? Holy crap. It's going pretty quick. So remember, we'll have our first exam coming up in not too long, right? I think it's, what is it, 21st? Is that what it is? Right? So, yeah.
Yeah, it's the 21st, but that's on a Tuesday.
Yes. Right? So, what we are doing this semester, right? We used to have our exams during lab times. We are having evening exams this semester is what it is, right? So if you take a look in the syllabus, we got some evening exam times for you there, right? So the 21st, between the hours of, we have blocked out 6 and 9 o'clock. It's not going to take you guys 3 hours. I'm not going to write you guys a 3-hour exam, although you're welcome to take that time if you want. That's when our exams are going to be, okay? So we did that just to kind of accommodate some issues that we had. We used to have to take exams in the chemistry labs themselves, but that's not very fun when you got to move squirt bottles and stuff around for you guys to be able to take exams. So we're doing evening exams with all the Gen Chem students this semester is what it is. That doesn't mean you guys aren't taking, you know, it's not a group exam. You guys are going to take the exam that I write for you, but it's on those evenings there. So a couple of quick points. If you take a look, right, go ahead and put the 3 dates for the exams into your phones, right? That way you guys have a reminder of when they are. They're going to be on Tuesday evenings. We're going to be in the big conference, in the big lecture hall in the academic building is what it is, all right? And if we have to have some overflow, we'll find some room for everybody there, okay? So aside from that, we'll talk a little bit more about it as we get closer to it, what's exactly going to be on the exam and those kind of things. I need to know about conflicts for those times, though, as soon as I can, so we can accommodate for that as it is, right? So come chat with me sometime if you know you're not going to be there for an exam, is what it is. All right, everybody with me on that? So evening exams, come get it done, rip the Band-Aid off, that kind of thing. Yes, ma'am.
Do we come to the place to take it, or is it on lockdown browser?
No, we're going to be doing paper exams, is what it is. Yeah, you guys will be in the rooms there. So, yeah, I don't know. I was never a big fan of the online exam stuff. They just kind of seemed to cause a little bit more problems than I enjoyed, and then the whole uploading work and that kind of thing. I like to see what you guys are thinking, right? Like with the quiz there. You guys all got zeros on the quiz. What's wrong with you? Right? Geez, everyone failed. No, I'm just right. I haven't graded it, right? So it's just going to show up as a zero. So remember, I'm taking a look at what the work that you guys did and that kind of thing there, right? So don't worry, you guys aren't. No, it's so all that stuff. Like I said, most of it, for most of the quizzes and things, I'm going to have to go through and kind of check on what you guys are up to there with that. So don't worry too much if you all of a sudden see a really bad grade online. Like I said, I have to go through and fix that stuff, and then we'll get your actual grade there up. Sound fair? But yeah, what's up?
Sorry. So you said the test starts at 6?
Yeah.
Okay.
Yep. But anyway, how'd the quiz go? Okay-ish, right? Not too bad, nothing too unexpected. One of them was a little bit tricky, right? The one about the volume of air and I think what was it, like the mass of air in a room or something like that is what it was, right? The question number 4 there. Very tricky place where I got that one from, the end of the chapter. So like I said, I'm just going to be taking stuff out of the book, right? So that's meant as a reward for those of you who are working on and looking through the problems there, that kind of thing, right? So I'm not looking to be too creative with my questions, although I do change numbers around and that kind of thing, right? But I promise I'm not going to show you guys something on an exam that we haven't talked about in class, right? The question might look a little bit different, but the theory and the concepts are all the same. My goal is not to test you guys on things we've never learned before, right? That doesn't assess anything, right? It's to test, hey, remember we talked about unit conversions. Have you been practicing those, right? So for the exam, right, obviously it's not going to be open book and those kind of things, so make sure you know those metric conversions and have those down, right? You got plenty of time between now and then to get them tattooed, right? That's perfectly fine. I'm not going to make, okay? Don't do that, please. Well, anyway, whatever. You're adults, you can make your own decision. I need to get an A, got to get ink. All right, so, all right. Let's see, anything else? You guys have labs this week, yes? All right, so don't forget to keep up with that also. You guys are using like that online system with Top Hat. Is that what you guys are doing? How's that going, by the way? Yeah.
I don't like it.
Don't like it too much? Is it giving problems or?
It just like takes a long time to load and like, I don't know, it just seems really like slow, and then I don't like having to write down again everything I already like wrote down.
I see, okay.
But like, yeah.
Okay, no, it's something new, so, hearing kind of what your guys' thoughts are. I don't have any, any stake in the game, so to speak. So I appreciate the genuine feedback there. Is it slow because of the website or because of?
I think so. I think it's just slow.
Okay, fair enough. Well, we'll go keep that in mind when we decide what we're gonna do next semester and next year with these things, so. And, like I said, and not to get too far off topic here, but I always do appreciate genuine feedback from the students, because, what you guys think and what you guys do influences how we move forward for the next year and the next semester and that kind of stuff also, right? So if there's something that's really grumbling at you there, just come let us know and we can see how we can help you, right? That's my job. My job is to help you guys out, right? I can't fix the cafeteria food necessarily, right? But I'll at least listen to you if you want me to, so. Sound fair? And I'll buy you a bag of apples. How's that sound? Good? Or a banana. I don't want to discriminate. There we go. All right. So, all right. So let's get started with prayer, and then we'll continue on to chapter 2 here. But Lord, we just thank you for inspiration. Lord, we thank you that you've given us the capacity just to take in the world that you've created around us and just use it to develop something new, Lord. Whether it's just a thought in our mind or just something to share with those around us, or a piece of art or a piece of science or whatever it might be, Lord. You've given us creativity, you've given us inspiration, and we know that's a gift that comes from you, Lord. Lord, we just pray that we can use all the gifts that you've given us to just glorify you in your name, in whatever way that might be, Lord. We pray that you help us to be good and faithful servants and just to use everything that we've been given back for your glory, and to share it with our friends, our family, our neighbors, whoever it might be, Lord. We just pray to be given those opportunities. We pray just to share you with somebody, the glory that you've done in our lives today, Lord. And we ask all this in your name. Amen. All right. So this is what we talked about last time, right? We were going through and we were discussing the way that we're going to name something, right? And we had two broad naming classifications. We said there's organic naming, which is next year for you guys going on to organic chemistry. And we had inorganic naming, which is what we're going to focus on in here, right? And we said within the realm of inorganic, we're going to talk about covalent and ionic compounds, okay? And so the first one we learned about is covalent compounds, and the important thing, the key thing, I asked my seniors this, okay? My senior biochemists, and they didn't get the answer right. Okay, one of these key things, we have to be able to recognize covalent versus ionic compounds. If we're dealing with a covalent compound, it's a nonmetal bound to a nonmetal, okay? Where do we figure out how things are nonmetals or metals? We look at the periodic table, got it? So knowing the broad classification about where metals and nonmetals are in the periodic table is extremely important. If we have two nonmetals, we have a series of rules to name those, right? We name the elements in the order they appear. We use the prefixes to indicate how many there are, and the assumption, where is it? Yeah, point number 3. The assumption that we make with covalent compounds is that they are invariant, okay? They're always going to have the same charge to them, and that's what we're going to talk about today. What do we mean by variant versus invariant, okay? And so from there, we progressed into the idea of ions, right? So if we're not covalent, we're ionic, right? Ionic is defined by a cation and an anion, something positive and something negative, okay? And cations are typically non-metals, cations are typically metals and anions are typically non-metals. We did some prediction of charges here, okay? I think this should be in your notes still, right? We went through and said, hey, can we start to predict charges, based off of what we see in the periodic table? And we learned about how to count to 8, right? The octet rule at the bottom there. Now, we might not have figured out exactly what we mean to count to 8 yet, but that'll become clear. So what we said is, let's get to the nearest noble gas. Let's take the least amount of steps to get to the right-hand side of the periodic table. We walked forward, we walked backwards, and we came up with the charges for our compounds here. Right? Excuse me, not our compounds, our elements. And I think this is where we ended up here, right? I think this is the last problem we kind of took a look at. We looked at aluminum, right? We said, okay, how many protons and electrons are in there? And I made the point about paying attention whether we're gaining or losing electrons. When we gain an electron, we become more negative. But in our minds, we think of negative things as losing something, right? You have a negative bank account, you have less money, right? But that's not quite how it works in here, so just be careful when you guys are doing your math. That's all I'm trying to get you guys to point out with this, right? So the only thing that we can gain or lose are electrons. Fair? Everybody remember all that? It's been a long weekend, right? 2 days off. Now you have to work on Labor Day. Geez, what kind of place is this, huh? Here we are. So I think the next slide is some more practice. All right. So similar to what we talked about last time, see if you guys can go through and predict the charges for these elements here, okay? Based off of where they are in the periodic table. Predict the, let's say, the ionic charges for these. It looks like you're doing it in reverse here. Adding versus removing electrons there. Guys are really quiet today. So I can whisper, right? Okay. You're still sleeping off the weekend, is that what it is? Big Ave Maria Labor Day parties. Okay, that's good. Yeah, like I said, it's not like it's wrong, but just unbelievable. We're gonna do these balance charges. Yeah. Cool. All right, so it looks like everyone's kind of stepping in the right direction there. So what we're doing, remember, is if we're here for nitrogen, that's where we end up, or excuse me, sorry, that's where we start, right? And we want to take the least amount of steps to get to our noble gases. Okay? So the book talks about noble gas configurations and octets and these kind of things, right? So we want to get to the right-hand side there, and the least amount of steps. So we start at 7, right? And we want to get all the way over to 10. So let's see how we do that. We do 1, 2, 3 steps to get there, yes? So we could do 3 steps forward, or we could do 1, right? 2, 3, 4, and then all the way back up to here to 5, right? So 3 steps forwards versus 5 steps back. You guys want to run 3 miles or 5 miles? Do both, right? Just get extra fit, yeah? No, okay. Which one do you guys want to do? 3, got it? Now if I move to the right, Am I adding or losing electrons? Adding, right? I add electrons, I become more negative. Got it? So I go from 7 to 10, there's a difference of 3 electrons. I add 3 electrons, so I have a 3 minus charge. Everybody with me on that? So I take 3 steps to the right or 5 steps to the left. What's 3 plus 5? Okay, is that a coincidence? Probably not. We'll talk about that though. Good? Everybody with me on that one? Let me just erase this real quick. Our good old buddy beryllium right here. Same assessment. We can go to the left, we can go to the right. We can either go forward or we can go backwards. We can take 6 steps to the right. Or we can take 2 steps back. Which one do you guys want to do? 2 steps back. That means I'm losing electrons. Right? If I lose electrons, I should end up with a positive charge. Got it? That's all we have to do, right? Forward versus backwards. Arsenic. Over here. Okay? 3 steps forward. Or, now you'll just have to bear with me here for a second. Right? 3 steps forwards or 5 steps back. Do you guys see the 5 steps? Oh yeah, Dr. H, you skipped that whole big thing in the middle there, right? So this is one of these things that we'll learn in just a minute. Okay, well, not just a minute, in a couple chapters, okay? Where do we get this octet rule thing? Why do we skip that big chunk in the middle? But even if you don't see that quite yet, right? The point being what? I can take 1, 2, 3 steps forward, or 1, 2, 3, 4, blah, 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 all the way back. Which one's going to be easier? The 3 steps forward, okay? Now I want you guys to think for a second here. What is the relationship between nitrogen in red and arsenic in yellow? They're in the same family, right? The same group, the same up and down. Why? Why, right, do we arrange the periodic table in the way that we do? Is it just circumstance, right? We just threw a bunch of darts and say, well, we'll just put this one here. That seems cool, right? That one looks kind of shiny. It's a metal. I guess we'll put it over here. Is that how the periodic table is arranged? Absolutely not. It's arranged by families. Okay? We talked about that a little bit in chapter 1 and at the beginning of chapter 2 here. Now, what do we know about families? Well, we're pretty similar to each other, aren't we? All right? If you guys have brothers or sisters or siblings, right? Are you pretty similar to them? I mean, you might not admit it to them, right? But I've got an older brother. Okay? He's 2 years older than I am. You want to guess what his job is? He's a chemist. Okay? He's a dork just like I am. Right? Now, he's not a professor, which makes me objectively better than he is. Okay? But he's a chemist and he works in industry. Right? So we have a lot of things in common, but are we exactly the same? No, of course not, right? It's the same thing with the periodic table. Nitrogen and arsenic have a lot that they share in common. For example, they have similar ionic charges. We tend to see nitrogen and arsenic have the same 3 minus charge. You guys understand what I mean by this? Does it mean they're always going to behave the same way? Absolutely not, right? But if you're stuck on the MCATs, right, and you forget everything that you learned about chemistry, right, but you remember that, well, I remember that guy ranting about nitrogen and a 3 minus charge, but I can't remember how to do it, but here's arsenic, right? If you know how to deal with one thing in the family, chances are the rest of the stuff in the family is going to behave in a similar way. Is everybody with me on this? This is one of these key things that's very, 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 very important. I can't teach you how every single element of the periodic table reacts. But if I teach you how nitrogen reacts, you guys can say, well, I think arsenic's going to be very similar. And this is one way that we can look at that. Everybody follow with me on that kind of that's the idea there? It's important. Okay? Cool. Bromine. Here's everybody bromine right there. I'll skip the yada yada yada. Hopefully we see that we got bromine 1 minus. Good. Are my answers correct? Do they make sense? Like, well, we did the step left, step right, run 3 miles, run 5 miles. What did we say about ionic compounds? Cations tend to be formed from metals. Anions tend to be formed from nonmetals. Okay, we got nitrogen. Is nitrogen a nonmetal or a metal? Non-metal. It's over to the right-hand side there. Did we predict it has a minus charge? Yes. Does that make sense within the context that we know? Sure. Beryllium, metal or non-metal? Metal. It's on the left-hand side. We predicted it to have a positive charge. Does that make sense? You guys get what I'm doing with this? I know we all get excited when we get an answer and you're like, oh gosh, it's one of the multiple choice, thank goodness, right? But always go back and think about what you're doing, right? I don't just give you a lot of information just to kind of, for you guys to go win trivia games at the bar, right? This is stuff that we need to use to solve problems. Stuff that we use when we're trying to figure out new science. Metals typically make cations. Non-metals typically make anions. Something good to pay attention to, something good to remember. Fair? All right. Okay. So dealing with monoatomic ions, that's what we've been dealing with all along, just single atom ions. Okay. What is a variant metal? Most of the variant metals are the transition metals. Okay? Excuse me, most of the variant ions, I should say. Most of the variant ions are the transition metals. Now, if, I know you guys are kind of copying something down for just a second, let me scroll back here. If you're looking at the periodic table, this stuff in the middle is your transition metal block, okay? That stuff that's in between kind of the two ends there. That's your transition metal block. So those tend to be variant. Notice I'm being very careful with my terms here, my words. They tend to be variant. Doesn't mean every single one of them is variant. New. Okay, we've got a couple exceptions here and there because otherwise life would be too easy. So we've got to make sure we try and trick our students. Make sure that they miss lots of points. Great. Just kidding. I'll show you guys where the exceptions are. Okay. But most of those in there, the vast majority are variant. Why do we call them variant? Well, that's what point number 2 is. They lose a different amount of electrons, depending on what they're reacting with and how much they are reacting with. Okay? Are they reacting with 2 chlorines versus 3 chlorines? That's going to lose a different amount of electrons. That's the difference. Okay? The group numbers that are on the periodic table are not too helpful with the stuff in the transition metal block. Outside of the transition metal block, it's extremely helpful. Okay? So, example, we've got titanium. Titanium typically exists in titanium 2+ or 4+. Chromium's got a whole bunch. I don't need to read all out. We got iron, we got copper, we got manganese. There's a ton of them. They have a bunch of different charges. Okay, they're all over the place. And I need you guys to memorize all those charges, right? No, good. I don't need you to memorize those charges because they're variant. How could you memorize something that changes all the time? Well, Dr. H, you underestimate my power to memorize things. Okay, fair, right? But don't do that. Understand how we can get the charges. Listen, here's the key part. We're going to do a couple examples and we'll see it again. But the way to know whether manganese is 7+ versus 2+, it's going to depend on what it is bound to. Something variant is always going to be with something invariant. Got it? So if I know what the invariant is, guess what I can figure out? The variant. Because what's the rule of life when it comes to ionic charges? Everything has to balance. Got it? If I have a manganese that's +7, I better have things that add up to be what? -7. You guys with me on this? That's all it is. Good? Yeah.
Invariants bond to variant.
Yep. Pretty good with that? So the magic is going to be adding things up to 0. That's how we're going to figure out the charges on our variant metals. So here's just kind of a broad, very, very broad brushstroke breakdown of the periodic table. Here in the blue, right, is where we tend to see our variant metals. Of course, I can't list everything in there. Okay. You'll notice there are some oddballs, like mercury, right? Has some weird different ions to it, and we'll talk a little bit about this in just a couple slides, right? You can see the purple over here are non-metals, right? We can see the charges that we've been predicting. Although I know on Friday somebody asked about what about carbon in the group 4 there, right? Here it says that carbon's going to be 4 minus, but carbon can also be 4 plus, depending on what it's bound to, right? So that's kind of the weird part of this. If I have carbon bound to oxygen, okay, carbon's going to have a 4 plus charge is what we would say, okay? Carbon bound to hydrogen, it's going to have a 4 minus. So we're going to have to learn a little bit of a skill in there to kind of figure out when some of these, let's say, oddballs are 4 plus or 4 minus, okay? Remember, there's always a couple exceptions. But our variant metals are there in the middle in blue. Okay? Our non-metals are over here in purple, and we should be able to predict those very easily is what it is, okay? With me so far? Okay? Let's see if there's anything important on this slide here. See, did I put something big and red and bold and important? Oh, there it is. It's at the top. Okay? I say this every semester, and I can't come up with a better way of saying it. I try to avoid having you guys memorize things as much as possible. Okay? My promise to you is that if I ask you guys to memorize something, it's because it's important. Not only for my class. That's not my goal. Okay? My goal is not to, have you guys memorize things for me. Right? It's memorize things for you to use in other classes. A lot of you guys have to go through more chemistry. A lot of you guys have to go through biology, okay? Or microbiology or cell biology, all these different things. You're going to see these polyatomic ions over and over and over and over and over and over again. They are in every branch of the, let's say, the natural sciences. If you're going into geology, do we even teach geology here? I don't think so, right? No rocks. Rocks don't exist. Okay. So but if you're going to graduate school for geology, let's put it that way. Right? You're going to see these over and over and over and over and over again. They're just everywhere. Can't get away from them. So what do I expect you guys to be able to do? I need you guys to memorize these. Now, why, Dr. H? Why? I've got too many other things that I need to know. Remember, the goal of Chapter 2, or one of the main topics that's going to show up on probably every exam in some manner, is that you need to know how to name things. Okay? What I need you to know about these are the names, because we're going to use those to name compounds. I'm going to say, hey, I've got sodium nitrate. And what you guys need to know is, what is nitrate? And what is sodium? And how can we put those together to make an ionic compound? Everybody clear on this? So I need you to know the name, and I need you to know the formula and the charge. So know everything on this table. Oh my gosh. Well, good news. Okay? The good news is that there are hundreds of people taking general chemistry, not only this semester, okay? But there's thousands, I would even say maybe millions, who have taken general chemistry throughout the years. And this is a very common thing that everybody, chemistry professors typically expect their students to memorize. So there's lots of nice quizzes online, there's resources, there's all this kind of stuff for you guys there, okay? Now, as with most things in life, this isn't arbitrarily thrown together, okay? Remember, science is based off of logic, for the most part, right? So there is a logic behind the names here. There's a logic behind the charges here. Once you guys kind of sit down and start to break this down a bit, you'll start to see the patterns that come out of this. It's unfortunate that in general chemistry, we can't spend too much time working on your guys' pattern recognition, okay? Because that's one of these key important things to becoming a scientist, no matter what field you're in, right? We see something happen in nature over and over and over and over again. We see there's a pattern, and then as a scientist, you say, I need to figure that out. Okay? But here's one of these examples, and we'll talk a couple of slides through these here. But it's not as big or an onerous a table as you guys might imagine at the beginning. Okay? There is a logic behind how it's written out. And this is coming from the textbook, although, geez, I forget exactly what, anybody have their textbook with them? If they can look up, if you get a quick second, could you just look up what table this is in? Or I'll do you real quick, while you guys are kind of admiring my ability to look through a book. Oh, it's also right in the back. So, there it is. If you open it up to the back, it's there. And then let me look up polyatomic ions real quick. Polyatomic ions, page 61. Let's see what page 61 has for us. Nothing. It's around here somewhere. I'll look it up for you. Oh, there it is. I'm sorry. Nope, that wasn't it. I'm getting close. I can smell it. Okay, so starting on page... You didn't hear that, right? Starting on page 68 is where it goes through all the information about the polyatomics. So page 68 through about 71 is what it is. Sorry. Good? All right. Like I said, my notes are always online for you guys, so you don't have to worry about copying this down necessarily here, but it should be useful to have. Okie dokie. All right, so just as a quick example, right, as we can kind of start to think about how we're going to pair this stuff together. So remember, we're dealing with ionic compounds. So we have a metal and a non-metal. We have a cation and an anion. We have something positive, we have something negative. And the charges have to balance. Good? The name for the polyatomic ions are the names that we use when we're naming the compounds. So, if we take a look at the top left-hand side there, we got CaCO3. Well, Ca is calcium. Where is calcium on the periodic table? Find it for me. Is it on the left-hand side or the right-hand side? Left-hand side. Is it a metal or a non-metal? Metal. Okay. Why am I asking you guys this question? Because one of the key things you have to identify is what? Covalent versus ionic. Got it? What's the difference? Covalent is non-metal and non-metal. Ionic is metal and non-metal. With me? Calcium's a metal. On the left-hand side. What about our good old buddy carbonate? Now our polyatomic ions, right? They are ions. We can consider them, for our purposes, to be non-metals. Although there are a couple of oddballs in there too, okay? I'm not trying to trick you. I'm just trying to give you how does 95% of this work, okay? Everybody with me on that one there? Right? We can consider them non-metals for our purposes. They will always make ionic compounds. That's what I'm trying to say. Good? Take a look at the previous slide. Take a look in your book. What is carbonate and what charge does it have? Carbonate is defined by what? What's its formula? CO3, 2 minus. Got it? Is that ever going to be different? Will carbonate ever change? No. You guys get why I'm telling you this explicitly? If I tell you something doesn't change, in our scientific terms, we would call that invariant. Good? So this is one of our defined ions. Carbonate will always be 2 minus. Always. Always, always, always. Forever and ever. Okay? Now, carbonate is invariant. What do we know about calcium? Is it in the transition metal block? No. That also means that calcium is invariant. You guys with me on this? Remember, if we're ionic, we have variant versus invariant naming. If it's invariant, you have to identify that. If it's variant, you have to identify that. So we have something invariant and we have something invariant. Good. Then all we do is call this calcium carbonate. Do the charges balance? Calcium typically has what charge? 2 plus. Carbonate has a 2 minus. Does 2 plus and 2 minus balance out? That's all we have to do. That's what I'm asking you guys to do. Everything that I just ran through there is how you guys should approach these types of problems. Is it ionic? Is it covalent? Is it variant? Is it invariant? What are the charges? How do I balance them out? Good? Over here, we can go through the same process. We have calcium, we have sulfate. Calcium's invariant. Sulfate is one of our polyatomics. Calcium has a 2 plus charge. Sulfate always has a 2 minus charge. Okay? So we call it calcium sulfate, and we go on with life. That's not too bad, right? What's the tricky part about naming these? Well, you have to know your elements on the periodic table. You have to identify whether they're metals or nonmetals. You have to identify their charges, and you have to know the names of the elements, right? Ca is calcium, not carbon, right? That's the kind of thing that I'm saying. Good? Cool. Down here at the bottom, something a little bit different. So here we have calcium phosphate. Calcium's invariant, phosphate is invariant. What charge does phosphate have, though? It's one of your polyatomics. 3 minus charge. What charge does calcium have? 2 plus. Do you guys see the problem that we have? So if I'm just looking down here at calcium phosphate, ooh, it's a bit excessive. Right? You told me that calcium has a 2 plus charge. And phosphate on its own has a 3 minus. So if I just take one calcium and one phosphate and I put them together, what do I make? Problems, right? You guys with me on this? Here's what I'm saying. If I say that calcium phosphate is just this, if I say calcium phosphate is just that, what's the problem with this formula? The charges don't balance, okay? But I really just want it to balance. Just make it easy for me, Dr. H. Okay, I will. How do we balance this? Okay, so we have charges that don't immediately balance by directly mixing 1 and 1. How many calciums do I need to balance out a 3 minus charge? 3. How many phosphates do I need to balance out a 2 plus charge? Is that a coincidence that one needs 3 and one needs 2? No, right? In fact, this is what the book talks about. It talks about crossing the numbers here, right? So take the 3 minus down for the calcium, right? And take the 2 plus down for the phosphates, okay? So we end up having, let's see if I can get my colors right here, calcium 3, right? And I did this in purple, PO4, in parentheses, 2. You guys see what I'm doing here? I'm just dropping the charges down, right? Finding a common numerator, basically, right? The common number between those. Everybody with me on this? That's all you have to do with it. If, as a quick note, right? If you have multiple of a polyatomics in one formula, make sure you put parentheses around those. You guys with me on that? That indicates we have multiple of the phosphate ions in there. Balancing charges is important. Remember, we're going to learn how to name things. So I'm going to give you a formula, you have to name it, right? Or I could give you a name and you guys have to go back to the formula. Both directions. Fair? But that's all it is, okay? Comfortable with that so far? Have to know charges, ions, that kind of thing, okay? All right, let's talk a bit about ionic compounds since we're going to learn how to name them, okay? Some of these topics we're going to come back to as we move on through the semester, as chemistry always does, right? Ionic compounds are held together by electrostatic forces. Now, what in the world does that mean? That means that they're held together by charges. Wow. Okay? How does all of chemistry work? Well, all of chemistry works by something negative being attracted to something positive. That's literally all it is. That's why I chose to be a chemist. Why? Because I can remember one thing. Okay? Find something negative, find something positive, and bring them together. Okay? Now, your immediate question is, well, if that's all there is, how come my book weighs 2,000 pounds, right? There's got to be more to it. And there is, of course, right? But if you're ever stuck on something, especially in the world of organic chemistry, this plays out every day, but even in general chemistry, if you're ever stuck on something, how does this reaction work, or what's going on here? Find your negatives, find your positives, find your electrons, find your protons, that kind of thing. Start to bring them together in a meaningful way, okay? So that's what I mean by electrostatic. The negative end of a magnet is attracted to the positive end of a magnet. Okay? Electrically neutral, this is what we were just talking about. Everything has to be charge balanced. The calciums and the phosphates have to be there in the appropriate ratios. Okay? Cations and anions attract each other. Well, we just talked about that. Larger charges are equal to larger attraction. The bigger the magnets, the stronger they're held together. That's going to be important. We're going to talk about how molecules talk with each other. Okay? And we're going to relate that to things like the melting point and the boiling point and the solubility. But the bigger the charges, the more attraction there is, it changes that property. Or not that property, those properties, I should say. Larger separation equals lower attraction. That's going to be based off of atomic radius is one thing. And so we'll talk about radius a bit more as we go through the semester, okay? But phosphate has a different radius than sodium does, right? Potassium has a different radius than sodium does. And that's going to change the properties and how things react with each other. It's all based off of Coulomb's law there. We don't have to worry about that value that formula there. In fact, I'm pretty sure it's on your equation sheet, right? But we could calculate the attractive force between ions if we're given the appropriate values is what it is, right? I don't think I've ever given a single problem on an exam that uses that equation. But that doesn't mean it's not important, it's just kind of working behind the scenes is what it is. The bigger the Q's, right, the bigger the charges, okay? That's what I'm trying to tell you. The bigger the numbers up here, the more force we have between those ions. So if I have +4, +7 on the top there, I'm going to make a bigger F. Got it? That's all it is. So this is kind of showing you what we just did on the previous slide there, right? If we have magnesium and fluoride, right? We have a 2+ and a 1-, right? If you take the 2 down here and the 1 down here, right? Magnesium fluoride is what we get out of that. Yeah?
What is the constant in that equation?
What is a constant? The actual number?
Yeah.
I don't remember. I have to look it up to be honest. It's just a constant is what it is.
What does it represent?
What does it represent? I mean, it's a constant that makes the equation solvable is what it is. It usually comes out of making the numerical, excuse me, not the numerical values, the units balance out. If we're trying to get, I don't know who asked the question, but who asked that question? Oh, the unit, okay, I'm looking at it, right? So if we're trying to get things in units of force, right here we have typically uncharged, I swear what's the word I'm looking for? The units. We have unitless values of charge, we just have plus or minus. And down here we have distance, right? So we have to have unitless over distance times this to get a measure of force. That's typically how constants are derived, right? Units of force are not per inverse nanometers, right? That doesn't make sense. So that's usually where constants are kind of derived out of from that, just to make sure the math kind of works out. Does that kind of make sense?
Yeah.
I will always give you guys a constant like that if that's what it is though. Okay, so here, right? Magnesium 2+, sulfate 2-. We can put one of these with one of these to make magnesium sulfate, okay? Similar to what we did on the previous slide, magnesium, phosphate, 3 and 2, right? Is everybody following along with us? The whole charge balance, crossing, right? Crossing the values of the charges there. That's how you guys are going to figure out how much of each one to put in there to balance it out, okay? Good. Okay, let's do a quick example. Let's say I have something called magnesium oxide. That means Mg and O. What would be the chemical equation for magnesium oxide? How would you approach this? So if I give you a name and we have to translate it into a formula, right? How do we go about something like this? Well, you pick up your phone, right? You go to Google, you type in magnesium oxide and say, okay, yeah, I would have gotten that, right? Is that how it works? Okay? What do we need to know? A couple of important things. Magnesium and oxygen. We need to know whether it's covalent or ionic. Is magnesium a metal or a nonmetal? Metal. Oxygen is a nonmetal. So we have a nonmetal and a metal. So we are ionic. If I know I'm ionic, I have to know the charges. Okay? How do we figure out the charges? We look at the periodic table. Okay? Is magnesium variant or invariant? Invariant. So I always know that magnesium is going to be 2 plus. Got it? Okay, so magnesium is 2 plus. We can write that down. Oxygen. What do we expect oxygen to be? 2 minus. How do we get that? Looking at the periodic table. Okay? Good? So we do Mg2O2 because we just brought the 2 down like that, right? You can, but when we write chemical formulas, we typically want to put the least common denominator there, right? The lowest integer value of how we can balance things out, right? So by convention, right, you would just put Mg and O. Everybody with me on that? Good? Ionic, covalent, variant, invariant, charges, periodic table, yada, yada, yada. Okay? We'll have some more practice coming up. Cool. All right. Still on the naming stuff. All right. So now that we talked about our polyatomic ions, let's talk a little bit about our monoatomic, okay? Monoatomic cations here. Okay, so monoatomic cations. What are we dealing with? Most metals are, most metal ions are positive, okay? Got that? That's something that we've established already. If we have a metal ion with only one charged state, aka invariant, how do we name that? The simple name for a monoatomic cation that is a metal is just simply the metal name plus ion after it. Ta-da! Chemistry, right? If I have a metal ion with multiple charges, aka variant, I give the metal name plus in parentheses the Roman numerals of the charge. Okay? This is important. If I am variant, if I'm in that transition metal block, you have to specify the charge. You specify the charge in parentheses with the Roman numerals. Good? So here we go. Examples. See what what you guys come up with. Well, let me do the first one with you guys here. Or I'll do these two with you here. So, looking at the left-hand side there. Top, Na. Na is sodium. Is sodium variant or invariant? Invariant. So it falls into the first classification there. So how do we name Na plus? We just simply call this sodium ion. Easy peasy, right? Down here, Fe. Fe is iron. Is iron variant or invariant? Variant. If we're variant, we have to specify the charge. We have a 2+ charge. So we would call this iron, in parentheses, 2 ion. Good? Do the rest. See what you guys come up with. Careful with aluminum, everyone. Is aluminum variant or invariant? Is it in the transition metals? I don't know. I don't have the answers. Do you guys have them? I didn't practice. It's my first day. There's aluminum on the periodic table. It's not a transition metal. If it's not a transition metal, we'll consider it invariant. So do we have to specify the charge? Okay. Calcium ion, aluminum ion. Iron 3 ion and lithium. Good? So if we just have a ion, for whatever reason, just floating around, that's all it is. I made a solution of sodium ions, right? That indicates I have a solution of Na plus floating around. Okay? I made a solution of iron 3 ions. I have a solution of Fe with a 3+ charge. Okay? So if we have monoatomic metal ions, here's the naming for it. The important thing to recognize is what we do with our variant metals and how we name those. Okay? Okay, we name the positive. Take a look at the negative side of things. How much time do we have? Okay. So, on the negative side of things, what if we have a monoatomic ion? We add IDE to the stem. So similar to what we saw with our covalent naming, right? we took our stem and we put the IDE at the end. Carbon dioxide, right? We took the stem, we took the IDE end. So similar to what we're going to do here, if we have a monoatomic ion, a single atom that is a negative charge, stem plus IDE. Now, if we're not monoatomic, we will be polyatomic. How do you name your polyatomics? Well, those are the ones that you have to memorize, right? That's the stuff in the table there. Good. That's the calcium carbonate that we talked about, the magnesium phosphate. Right, your phosphates, carbonates, permanganates, your peroxides, hydroxides. Those are all your polyatomics. You need to know those names so you can use them when you're naming the compounds. Okay? Cool. So what do we got? We have phosphorus. Okay? Typically it has a 3- charge. If I ask you to name this, we would call this the phosphide ion, right? The phosphide. Stem plus the IDE. Good? Sulfide. Stem plus IDE. Is this a single atom here? Is this monoatomic? No, this is monoatomic. This is polyatomic, so this is our sulfite. Yeah.
Are these anions?
Mm-hmm. Up there in the blue, there, the negative ions, the anions. Yeah. Everybody with me on that? A couple examples off to the right-hand side. So name these. What are the names for those anions there? One with the carbon's a little bit weird sometimes. Close. So that's actually just the U prefix there. Yeah. So monoatomic, monoatomic, monoatomic. Take the stem, IDE ending. So ox, ion, right? So the oxide ion. So carbon, we call carbide, okay? We drop the ON part of it. So the carbide ion. Nitrogen would be nitride. Sound good? Question. A little bit of practice here then. Let's say I have something called calcium nitride. What's the formula? Yeah. Can everybody do that? Look, these are the jokes, folks. You gotta take them as they come, all right? It's only so many words I can spell with the periodic table, right? You can spell nacho with the periodic table, right? There's something called acetate, that works out well. It's one of your polyatomics. There was a competition at one of the national conventions for chemistry, where if you could spell the biggest word using only elements, you would win some kind of prize, is what it was. So there are actually competitions. I can't remember what the longest word was, but it was certainly bigger than nacho. So a couple examples in there, but here we are. Anyway, joking aside, everybody good on this? Monoatomics, polyatomics, charges, balancing, yada, 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 yada. Yes? Okay. Got a couple more minutes with you guys, right?
2.
Huh?
2.
2. Is that not a couple? Thank you, sir. Just one more, I promise. Calcium nitrate. Now look. What is my ending here? The nitrate. Is the AT ending the same as the IDE ending? No, it is not. So watch, this is what I'm trying to get you guys to see. If you end in ates and ites, those are your polyatomics. Sulfate, nitrate, phosphate, carbon 8. Okay? So pay attention. Your IDE ending tells you something important. IDE endings mean they're monoatomic. Your ates and your ites are your polyatomics. Everybody catch that? That's a way to kind of check yourself there, make sure you're on the right track with this. Okay? Calcium invariant 2 plus. What's nitrate? NO3. 1 minus. So what's my formula for calcium nitrate? CaNO3 2. Good? That's the magic. Balancing the charges. Okay, see you guys on Wednesday.